Lab 1 experiment, I will be analyzing and modeling the constant velocity motion of a system, a children's toy soccer ball with mass m equals 0.3 kilograms, as it rolls across a flat surface. To do this, I will be applying Newton's second law. To establish an observed motion, I have placed my video in the tracker application. The shutter frame that I have used in my iPhone camera is 30 frames per second, and the subsequent frame delta t is 0.033 seconds seen here. I've also included a ruler at the bottom of the screen to establish a proper length scale, and I have also included the axes here, starting at the center point of mass in the first frame of the ball. If I were to flip these axes, it wouldn't necessarily change the overall outcome of the analysis, rather than the ball would just be moving in a negative x direction or so. The motion points along the x-axis in the positive direction along with the respective timestamps, and these are recorded via the point mass tool. So if I play this video, you can see the trailing dots behind the ball as it moves across the screen. These data points are stored in the table to the bottom right of the screen, and from these points I can derive the following. Our observational start time is 0 seconds. The initial position is 0 in the x coordinate, 2.119 e to the negative 3 in the y coordinate, and 0 in the z coordinate for meters. And we will be negating the z coordinate altogether in this point in this experiment, so that is accurate. The initial velocity can be observed as 1.22 meters per second, and the time of last observation is seen as 1.151 seconds. Using the findings from Tracker, I can then move to the GlowScript to model this constant velocity motion on the computer. This isn't seen in this startup code here, and I have changed a few of the values to match the data points that we have observed in the Tracker. So I've changed the ball's mass to be 0.3 kilograms, which is explained in the beginning of the experiment. The initial position is vector 0, 2.119 e to the negative 3, 0, which was seen in the Tracker data. The initial velocity is 1.22 in the positive x direction, 0 and 0, which is accurate because we saw the ball move in the positive x direction, 1.22 meters per second. Our initial time of observation is 0, so t equals 0 here. Delta t equals 0.033, which was established in Tracker. And moving to the while loop, the time of our last observation was t equals 1.151 seconds, and so this is going to be our limit for our while loop. Because we will be dealing with constant velocity motion, I have set the net force to be vector 0, 0, 0, because we are assuming no net force as we are dealing with a constant velocity. I've used these following equations for the final velocity and the final position of the ball, as these are derived from the Newton's second law. Final velocity equals initial velocity plus net force over mass times delta t, and final position is initial position plus velocity times delta t. And with all of these changes, we can run the program, and seeing this, it looks accurate, and the simulation and graph of constant velocity fairly resemble the one that is seen in Tracker. Now I can copy and paste these time and x position values into a spreadsheet, which are seen at the bottom here, along with the chart data from the Tracker observations. So here's our observed position and time from the Tracker, and here's our modeled position and time from GlowScript, and this is the line graph that I have gotten from these. After plugging in these values, it is evident that the predicted model and the observed position and time graph are not identical. At first, the models appear to trail each other, seen in the very beginning here. However, as time goes on, the observed model appears to stray away from the constant velocity and slow down as it increases time. Some possible explanations for this could be because we have negated the net force altogether, and this does not account for external forces such as friction that occur in real life that would slow the ball down as it rolls across the floor. If I were to go back and revise this model and make it more accurate, I would account for the net force, and I would change it to a non-zero value, one that accurately describes the friction placed on the ball. This also would help explain the ball's somewhat rough surface, and this may have contributed to the friction as well, as the ball is a very old toy that's been used outside for many years. This model is very important to consider, as constructing a model for constant velocity is important for its application to all sorts of movement in our world. This is simply the base for other applications of motion that we may explore through this physics class. Thank you.